In our previous lectures, we have encountered signals as squiggly lines changing over time. These lines represent a real-world phenomena like sound waves, radio signals, or electrical currents. But how do we get these signals into a computer? Transforming them into digital data our software can manipulate. In this lecture, we will introduce the fascinating world of digital signal processing, a field dedicated to capturing, analyzing, and reproducing signals using computers. Our focus here will be on sampling, the process of measuring the signals repeatedly over time to convert them into computer-friendly format. We will just scratch the surface of digital signal processing here, but don't worry, with a few foundational concepts, you will be ready to dive into hands-on world of software-defined radio. At its core, sampling is simply measuring. Computers require numbers to process information, and sampling involves taking a series of measurements over time to convert these analog real-world signals into numerical values. If you measure often enough and with sufficient accuracy, the resulting series of numbers will closely approximate the original signal. Each of these measurements is called a sample. Now let's start with a simple example. Imagine a signal as varying voltage on a wire. Over time, this voltage change 1.3 volts at one moment. It can be like negative 0.042 volts. The next, 110 volts after that. So, to represent this dynamic signal digitality, we must repeatedly measure the voltage, generating a sequence of numerical values that capture its changes. These measurements allow the computer to see and work with the signal. Analog to digital conversion. The device responsible for translating real-world signals into computer-readable values is called analog to digital converter. This hardware component samples the continuous analog signal and outputs a stream of digital values. Since the computers interpret the world in discrete steps, the analog to digital conversion's job is crucial in bridging the gap between analog reality and digital computation. The simplest signal you might encounter here is square wave alternates periodically between two fixed values. Now consider a square wave that switches from 0 volts to 3 volts every second. So if you feed this signal into analog to digital converter, it will measure the voltage at regular intervals, producing a steady stream of samples. And the samples could look like this, like 0, 0, 0, 0, 3, 3, 3, 0, 0, 3, 3, 3, 3, 0, 3, 3, and so on. So visually, we can plot these samples as dots on a graph. By connecting the dots, we did approximate the original square wave. Even though the digital representation is not perfectly smooth, it captures the essential features of the signal. Now you may ask, how we can sample the sinusoids? Sinusoids, these smooth oscillating waveforms, are fundamental in SDR and many other applications. When a sinusoid is sampled, the continuous analog wave is broken into discrete dots. Although these dots only approximate the original waveform, their arrangement still reveals the sinusoid's characteristic oscillations. Now, real-world signals like audio or radio waves are often more complex. When sampled, these signals also transform into numerical streams. For instance, an arbitrary waveform might produce samples like this: 1.0, 0.6, negative 0.7, negative 1, negative 0.3, and so on. Although the sampled version might lose some of the nuances of the original waveform, it remains a reasonable representation. However, understanding what details are lost and why it requires exploring topics like sample rates and precision, we will discuss that later. Just as we can digitize analog signals using analog to digital converter, we can reverse the process with digital to analog converter, DAC. A digital to analog converter takes numerical values from a computer and converts them back into real world analog signals. For instance, when you listen to music on your computer, the digital to analog converter translates the digital audio file into a signal that drives your headphones or speakers. In summary, while analog to digital converters digitize analog signals, digital to analog converters brings digital data back to the analog world. Together, these devices enable seamless interaction between real-world phenomena and digital technology. One critical factor in the sampling process is the sample rate, or how often measurements are taken. Sampling too slowly can result in an inaccurate representation of the signal, a phenomenon known as aliasing. On the other hand, sampling at sufficiently high rates ensure the digital version closely mirrors the original signal. We will explore sample rates and their implications in more depth later in this course. Analog to digital conversion is the gateway for real-world signals to enter the digital realm, while digital to analog conversion allows computers to output signals back into the physical world. Although this section only introduces the basics, these foundational concepts will serve you well as you begin working with SDR and other signal processing applications. For now, we will focus on understanding the flow of information, capture signals with analog to digital converter, process them in the computer, and reproduce them with digital to analog converter. I'm Typhoon, and I'm waiting you in next lecture.